Question 4. So now we're looking at association and numerical data, so some bivariate data analysis. And the first 2 marks come from plotting the last 5 points in the table here. So let me slide up and here's my bit of graph paper. When you look at it, that's a little bit sus, isn't it? Looks like we've got one set of possums here and another set of possums over here. But overall, if we look at all 10, you'd have to say that there's a decreasing trend, which seems a bit unlikely that the longer the gestation period, the smaller the possums are going to be. It looks more like there's a little bit of positive regression through 2 separate data groups. Anyway, we don't get asked about that. So here we go. We're given the correlation coefficient is about negative 0.6 and the least squares line here. And we've got to describe what the correlation suggests about the general pattern of association. Well, I've never heard of that before, but anyway, let's give it our best shot. So the correlation is negative, so that means that as one goes up, the other goes down. I think something like this for the 2 marks. It's not particularly strong, but there again, it's not that weak either. So we'd say there is some moderate negative association between the variables. And then we could elaborate using the gradient maybe to say that suggesting that for every day of gestation, birth weight decreases by 0.17 kilograms for these possums. And then over the page, so here we go, part C, determine the coefficient of determination. So that's r squared, so we've got to square negative 0.6, and 6 is a 36. The negative signs cancel out, and we've got 0.36. Then we've got to state the meaning of this number. So normally we turn it into a percentage when we talk about coefficient of determination. And so in the context of the question, we can say 36% of the variation in the birth weights, that's the variable on the y-axis, can be explained by the variation in the gestation periods, the variable on the x-axis. 1 mark for that. Then use the least squares line to predict the birth weight of a possum after 40 days. So we substitute 40 in, and again, look at this. We don't have a calculator, but we do our best. So 4 17s are 68, so this becomes negative 6.8. Then we've got to add 49, the y-intercept, to end up, so 49 minus 6.8 is 42.2 grams, all for 1 mark. What's wrong with giving us a calculator? So we carry on. Part F, we're asked to comment on the validity of our prediction. And if we just look back to the original set of data, this was for 40. So we can see that it's right smack bang in the middle of our data set. So it involves interpolation. But the correlation, where was it? Here it is. The correlation was very kind of iffy. It's only 0.6. So let's come back to this question. How valid is our prediction? We should treat it with caution because although it involves interpolation, the correlation coefficient of negative 0.6 indicates weak to moderate association. So for your 2 marks, we're always trying to get in whether it involves extrapolation or not, and on the strength of the correlation. Then, is there any statistical evidence to support the research view that a higher birth weight will cause a shorter? And the word here that causes the alarm bells to ring is the word cause. Yep, we know that there is no evidence of a causal relationship between the variables. All we've measured here is that there is moderate evidence of an association between the variables. So that would be our justification. We're going to say no, we've just got evidence of an association.